ladies and gentlemen, to this workshop. I believe I'm talking to students who are enthusiasts of AI and machine learning and the recent evolution of the tech world as it happens to do with artificial intelligence. Before we go into much details in what we are to learn in other sections of this workshop, I want to talk to you about basic mathematics for machine learning using AI. And so, I believe you've had an introduction of myself. I'm Dr. Ubong Samuel Idiong in the Department of Mathematics at the Federal University of Education in Nigeria. So let's go into why we are here. Whether you are coming from academia, industry, or pure research that make math behind AI less intimidating and far more empowering. So why does this workshop, why does it matter? Let's get real. Mathematics is the backbone of artificial intelligence. Behind every smart assistant, recommendation engine, or self-driving car, there are equations and various aspects of mathematics are employed, namely linear algebra, calculus, statistics, and optimization, working silently in the background. But why should you, as a scientist or engineer, care about this math in AI? Because understanding it will help you to be able to design smarter algorithms. You have confidence to interpret AI results. Not only that, you have the skill to innovate, not just use machine learning tools. So today, I'll break these concepts down. So by looking at number one, the core mathematical concepts for AI. Two, connecting maths to AI, so machine learning applications. Three, real world demos. Okay, because of the time limit I have, I will just make one or two applications. Okay, so we go number one to the core maths concepts for AI. Let's go. So number one, we see linear algebra. We call this the language of data. First, let's talk about linear algebra. If you can understand vectors, matrices, and tensors, you are halfway to understanding how data moves and transforms in AI systems. So when we talk about matrices, they are actually information that are coded in form of entries along the rows and along the column. So for vectors and matrices, the building blocks of data, you think of an image as a matrix of pixels, or data set as a matrix of numbers. Then the dot product and matrix multiplication. These operations lead to neural networks. Helps you to find patterns and make predictions. So then we have the third aspect, which we call the eigenvalues and eigenvectors. Have you ever heard of principal component analysis? This is how we reduce dimensions and reveal the structure of complex data sets. I will give you an example so that at least you will see. And where do we apply this? when you feed images into the convolutional neural network, it is a matrix operation. Linear algebra in action that extracts features and enable what you call recognition. Later on, I will give you an example of how you use matrices to extract facial recognition. Okay. Now let's look at an example here of matrix application to analysis of pictures. So matrices represent data sets where the rows, which are the samples, for example, images and users, and then the column, these are the columns, 1, 2, 3 columns, represent the features of these images, namely the pixels and the attributes. So when you implement this matrix, what it should give you, each pixel value is a matrix entry. This is a pixel value. This 255, 0, 1, 2, 3, 34, 254, and so on. These are the pixel values. Now let's look at the eigenvalue decomposition, its application. So the dimensionality reduction via eigenvalue decomposition is obtained using the transpose matrix multiplied by the matrix X, and that will be composed into a projective matrix. And this is the matrix of eigenvalues and the transpose of the projective matrix. So this is used in a way to also identify or code information about images. Now, next, calculus, specifically derivatives, gradients, and gradients. This is what powers learning in AI. Let's talk about derivatives and gradients, for instance. These measure how tiny a change in input affects output. So, and it is critical for what we call optimization. Okay? And in optimization, we are trying to, for instance, if you are into business, you want to maximize profit, and you want to minimize losses, or you want to minimize capital and maximize profit. All those things are involved. Then we also have in calculus another concept we call chain rule. Okay, this allows deep networks to learn layer by layer, adjusting weights through back propagation. Okay, then the third one, which we call the gradient descent. The main algorithm for training models, in machine learning, machine is trying to learn from intelligence, gather information from human intelligence. So it's what you put into it that it works on, and it gathers all over this information from various spheres, especially using the internet. So now, these deep networks will help you to learn layer by layer. Now, when you talk about chain rule, for instance, I think I'm still on chain rule, you will see that where one stops, another process begins. So that tells you that you take your learning layer by layer. So it helps you to adjust weight through back propagation. Then the third one is gradient descent. The main algorithm for training models here, taking tiny steps to minimize loss. So you don't just minimize loss all at once, but you have to do it gradually. So that is the work of gradient descent. Let's see the application of all these three concepts in calculus. There are more aspects of calculus that are useful in AI machine learning process, but these are just the three we are able to consider because of time. Every time an AI model learns, It's using calculus to treat parameters, okay, to change parameters and get closer to the right answer. For instance, when you are using AI, you seek or you probe AI for a certain information. It will not give you the accurate information all the time. And so you have to work on it, you have to continue to work on the data so as to get something that will be more accurate. So you don't just, you have queried AI to give you a certain information. You don't just, when it gives you that information, you don't just copy the information and make use of it. You have to critique the information. Is it near accurate? And there's a way of probing AI to be able to get a very accurate outcome. And so sometimes you have to use words like, give me something, an outcome that is near human predictability or close to what is obtainable in a perfect real-life situation. So by doing that, you will see that it will minimize error. So for example, when you see a neural network improve after each training work, that's calculus at work. You are minimizing error and you are optimizing the outcome. Now, we look at the third aspect, which we call probability and statistics. Okay, this is what we call the logic of uncertainty. Of course, we know probability dwells on uncertainty. Okay, so AI and machine learning thrive on data, and data sometimes can be very messy. Okay, so you need to collate that data, arrange it in a very logical way, and that is where probability and statistics come in. So for you to be able to process the data, you have to arrange the data logically. So how do we achieve this? Number one, we use what we call random variables in probability. You see, for instance, human beings are random. In fact, you have other concepts that are random. If you look at Brownian motion, for those people who are into biological sciences, fluid mechanics and all that, you do what we call randomness. Okay, the market, forex market, for instance, is very random because you cannot predict human behavior. And so everything you do depends on uncertainty. For somebody to enter a shop and he wants to make some purchases, he can get to that shop, he may decide to buy and he may also decide to decline the purchase of an item. So that is where probability of random variables come in. Now let's go to the internet, like predicting weather. Weather is a random event, and so because it's a random event, you cannot really be able to give full prediction. Okay, at so time, this is how the weather will look like. It may take a form. Maybe you have a cloud and you may say, oh, it will rain. But sometimes, while you see the cloud, it doesn't necessarily mean it will rain. Likewise, if you also are in the cold region, like in the US, in the London, in the upper hemisphere, you may say that this is the exact time that the snow will fall, and it may not always be. So, randomness, very important. Then you talk about probability distributions. These are mainly normal distribution, Bernoulli distribution, Poisson distributions. Okay, I'm going from the ones that are basically for finite sample and for the ones, small samples and large samples. So you use these distributions to be able to predict very large and even continuous data. Now we also have what we call Bayesian inference, where you have to carry out what we call conditional probability. And so you may say an event will happen preferred, if a certain condition holds. And so when you are using that, you are using Bayesian inference. Updating models released as new data arrives. This requires what we call Bayesian inference. So it will help you to update data beliefs, model beliefs as new data arrives. So then the fourth one is what we call hypothesis testing. This is very valid for validating models. How sure are we about our predictions? So this hypothesis testing will tell you, perhaps you are 90% sure, perhaps you are 95% sure, perhaps you are 99% sure. So hypothesis testing is very important. So you see all these are very important. Now let's see the applications. You see these spam filters. Okay, sometimes you receive a spam mail. Okay, you can either decline the spam or allow the spam to mail to exist. So those are the things you use probability for. Now, when you receive spam mails, you receive all kinds of mails. Some of them may be useful, some of them may not be useful. So you can decline and you can accept. Recommendation engines, okay, these also make use of probability. Then you also have risk assessment tools. Now, for those that are into financial markets, who are into stocks, who are into real estate, you need the knowledge of probability. In fact, what we call the stochastic analysis, okay, and stochastic analysis is built on the concept of probability, and this will tell you whether the rate, okay, the forex rate is going to be high, insurance is going to be low, depending on world events. Okay, so you are able to predict accurately, okay, what happens if war happens. Okay, what will likely be the impact on financial market? All these things will make use of statistics to be able to probe into them. Okay, then this, for example, naive bias classifiers use these concepts for text classification. So we have it for text classification. Then the last one is what we call optimization. This helps you to make models better. How can you improve on models? Okay, it is the work of optimization. For instance, if you happen to be in the 80s, okay, or in the 50s, you will see the television that you watch. Okay, now there have been several improvements to optimize the pictorial appreciation of all this television. Now, if you look at it, the quality of image production in all those implements, you see, they are not so attractive to the eyes. But due to improvement, optimization over time, so the noise have been weeded out. Okay, so what you now have is pure images. You have the 2D, then we move to the 3D vision. All these things are the work of optimization. Without optimization, we will not improve. In fact, when you look at the whole concept of humanity, human beings are concept in progress. All we are working at is working towards optimizing our potential, okay, so that we can get to what a state of perfection. Now, no AI model is perfect for a start. Okay, that is why you keep on seeing different generations of AI models. You have, for instance, the ChatGPT, the 3.0 and the improved to 4.0 and so on. Very soon we'll be talking of things that are very high. Okay, all those things are part of the things that optimization helps you to do. Optimization is the science of improving AI, for instance. Okay, now what are the concepts we have in optimization? Number one is the objective functions. What are we optimizing? Is it accuracy? Are we optimizing loss or something else? This is what we do in optimization. Okay, if you are in a business, you want to ask yourself, what do you want to optimize? Do you want to optimize your profit, and you want to minimize your loss? Okay, do you want to maximize and optimize the time, the outcome, and you want to minimize the time taken to achieve that? That is what modern tech is all about. You want to minimize the time, you want to reach the stars at the speed of light. You want to achieve things within very minimal time, and that is what AI is trying to do. Now you want to talk about AI trying to carry out very complicated surgeries. Okay, what time it will take a medical doctor who has been trained, that is a GP, general physician, or a surgeon, to be able to carry out that operation. It will take a lot of time for him to be able to achieve that. But all those things have been coded into the AI now. The robots can now do that job within a very short period of time. And that is what optimization is all about. Whatever you do as a scientist, as an engineer, you are aiming at how to optimize the outcome of whatever you do. Since the Industrial Revolution in the early 1900s, you could see that human beings have been working towards optimizing productivity. So that is what we do here. Not only that, we have the concept of convex versus non-convex functions. What do we use this for? Why training deep networks can be, this will help you to train deep networks, because it can be very tricky, so it helps you to remain within, to restrict, okay, the concept of what the outcomes of deep networks will be. Then we also have what we call regularization. This will prevent outfitting, and it keeps models generalizable. Okay, so then when you tune your models, the application, when you tune your models hyperparameters or add dropout to a neural network, you apply what we call optimization principles. So here's the key. For every piece of math, there's a direct AI application. Linear algebra powers computer vision. Okay, CNNS, that's the central neural networks. Then calculus makes neural networks learn. Then probability underpins algorithms like decision trees, Bayesian networks. And optimization is why your model doesn't just memorize data. It generalizes to new information. I'll show you a real demo, like predicting house prices with linear regression, visualizing neural networks, adjust weights and clustering data. But for the second one, I will use facial data recognition just for the second example. Okay, let's quickly look at that of predicting house prices using real world data. So now Where grid data is not available, we use hypothetical data. So we go to the Python that we constructed. So we generated a data here for housing prices, okay, because housing prices will determine will be determined, number one, by the size of the square feet of the house you want to get, okay, especially in very well planned societies like the US and the UK. Houses are not just bought, they are based on square meters and square feet, okay. These are the data we generated, and then we're able to implement, okay. And when you are implementing this, you will use what we call the statistical model, which we call the regression line model. So when you run this data, you are going to see the regression graph there. So we are able to plot the regression graph, okay. So this is what mathematics does, okay, when you come to the plotting of data, okay, of actual versus predicted house prices. You know, house, if you go into the real estate now, the actual prices you want to predict how within 5 years or within a year what will be the actual price of houses. So we go to the next one, which has to do with facial recognition. Now, when you stand before a camera or an AI facial recognition machine, what it does is that it will pick certain things from your face and it will record them as matrix data, okay. So let's look at this. We also generated this, okay. Number of individuals is given by that. The images per person is given by 10. Then the embedding dimension, okay, of each facial. So this typical dimension of facial embeddings is what we use, okay, for the pixels and all the rest. So now we look at the range per person, and then we embed the person's ID plus 0.5 random variable. And then we also look at the embedding of the person's ID. And so now when the machine is to analyze this, it is not going to put the whole face of all the people it has viewed. It will pick something unique to every person's face, okay. Maybe you have a pointed nose, you have very bulky eyes and all the rest. So there are certain things it will pick, okay, very large mouth, and then your complexion. And so it will pick all those things and it will use them for facial recognition. So let's see how this data comes out, how the machine interprets this data, okay. It's also going to interpret it based on dots, okay. So you see each person, there are 5 persons, okay, that the machine tried to recognize here. So each person has his own dots, okay, 1, 2, 3, 4, 5. And so based on this, that is what it will use to recognize your unique identity. So that is how we see that this is used. But these dots are formulated using pixels, okay. It will record this information in form of pixels, and these pixels are in a matrix. Please, let's see the matrix. The matrix, okay, that generates that image there. Okay, let's see the matrix. Okay, so we see the metrics here. These are the information it stores concerning each phases. So you see all the pixels are being used to form a matrix. Okay, so you see the matrix enclosure here is showing a block matrix. So thank you very much. That is how far we can go. So I want to find out if there are any questions in the house. Please feel free to ask questions based on what you heard. Yes, sir.
Thank you, Dr. Idiong, for your very interesting workshop or paper on AI and then in mathematics. I wish to know if while we get our prompts, suppose there are maybe I won't say error. If the prompts given to AI we have issues with such with respect to your desired result, yes, and then with respect to what we have done, will AI correct based on maybe it's able to identify there is an error in this prompt, or it will give us result based on the prompt given, or will it have the capacity to learn that, oh, this is supposed to be the input required for the result to be generated?
Okay, thank you. The answer to that question are two ways. If your information is adequate for AI to act on, it will give you outcomes. But it will not, if you were to if it gives you an outcome and perhaps you want to implement that outcome on another software, if there's an error in that outcome, that software will not run. It will complain that there are certain things that are required for it to be implemented. So AI will give you what you give to it. It's garbage in, garbage out. So, but you have to be an expert in your field. That is where you have what we call the human machine interactive learning. Okay, so now we are talking about what we call the age of singularity, where machine learning is competing with human learning. Okay, and we are looking at an age where machine will be more intelligent than human intelligence. Predictions are being made. I'm currently working on a research on that, okay, on prediction of human machine intelligence singularity. So machine is still subservient to what humans input into it. And so if you observe an error, you have to change your prompt if it is not giving you the desirable outcome. So you continue, that is, you continue to change your prompt until it optimizes to give you what you actually expect. Until you arrive at what you expect as your outcome, you shouldn't fully 100% rely on machine. So that is the answer I have for that.
Thank you.
Yes.
Thank you, Dr. Idiong.
Yes.
In addition to what the first person asked question, which means from your explanation, you are trying to tell us that despite the fact that we need AI, then as human, we have to do our work to a reasonable extent.
Yes.
Okay. So I want to ask that you mean if I have an idea that nobody have not been simplified,
Yes.
nobody has not worked on it to break it down, and I want AI to assist you, AI may not be able to assist. Are you saying I need to work on that thing to reasonable extent
Okay.
to bring AI in for further solution?
Okay, thank you. When we talk about AI, we are actually talking about machine intelligence. Okay? When you talk about machine intelligence, it collates data, all available data worldwide, okay, that of people's ideas from all various generations and even in contemporary times. Okay, so because human innovations are evolving every day per second, okay, per millisecond, per microsecond. Okay, so because of that, you may have a unique idea. Okay, now when you bring your idea to AI and tells it to implement your idea, it will only give you idea based on what is available. Okay, so when it gives you those ideas, which may not outrightly be useless, for every new idea you have, it can be built from an existing idea. Okay, so when you have that idea, you pose certain questions. I was trying to write a journal research paper, and from my interaction with AI, I observed that each prompt I gave to it, when it was new to AI, it would tell me that, wow, how could you think in such an intelligent way? It will first of all give me that commendation that I've given it something that it has not viewed before, and then it will start processing based on those queries, which we call prompts that you give to it. So that is just the situation. So you keep on building. It is the way you structure your question or your prompt that will help you to acquire more information on what you see. I was trying to solve a mathematical problem which has not been handled before, and I tried to prompt the AI to give me outcomes, and he told me, he said, I'm sorry, I don't have all the information about what you seek. So there are situations like that, okay, where it doesn't have such information. So it's very realistic. AI is very truthful. It will only give you what exists and not what he has not found. Okay, so it's a reciprocity of all human ideas and innovations. So you can only build on what exists. You cannot build on what does not exist. So every new knowledge or new innovation stems from an existing knowledge. So that is my answer to that.
Thank you, sir.
You're welcome. Any other questions?
Thank you very much. It's highly commendable. I know that every area that AI is very, very useful. The application is so wide. You talk about any field, AI is very resourceful and very useful.
Thank you very much.
Thank you, sir.
Congratulations.
Congratulations for the nice presentation.
Congratulations.